All right, day 2 of online learning. I hope you're excited. So many of you said you needed a review or refresher for drawing Lewis dot structure, so here we go. First, you should count up the number of valence electrons in the molecule, add them all together. I call that your piggy bank. Then we're going to arrange the elements. Usually you'll have one in the center, or it's going to be a chain. So we're going to start with more like either two things bonded together or one central atom, but you'll kind of arrange it so it's easy for everyone to bond. Then you connect with single bonds first, so you'll connect each element to that central atom, or if it's a chain, you'll connect the chain with single bonds. Then you're going to fill the outer with lone pairs. So we always will subtract from our piggy bank, and we're going to fill then the outer with lone pairs of electrons. And then we'll do the inner. And if there are lone pairs left, electrons left in your piggy bank, we are going to put those on the inner, or we might have to do multiple bonds to make that inner atom satisfied. And then we will check valence. So when you're totally done, you're always going to want to make sure that the elements should be, I put in air quotes, touching at least the number of valence electrons contributed. Ultimately, every element is going to want 8 electrons. They want to feel like they're touching 8. But I'll show you what I mean in terms of they should essentially, if they're contributing, for example, 6 valence electrons to the piggy bank, they want to be as near to those 6 that they donated as possible. So I promise I'll show you what I'm talking about once we hit an example where that comes into play. So some tips. First, you want to make sure the octet rule is followed. So when I said fill outer, fill inner, that's to follow the octet rule, which says all elements want 8 total electrons. There are some exceptions. Hydrogen is okay with 1 pair of electrons, which is usually the form of 1 bond. Beryllium is okay with 2, and boron is okay with 3 pairs of electrons. I say boron's a moron. He's okay with 3. If you don't have enough electrons in the piggy bank, so let's say we filled the outer and now we're going to go fill the inner atom, and he doesn't have 8 yet, but my piggy bank is empty, then we're going to add what's called a double or a triple bond. If I'm going to fill my inner electron and he already has 8, but my piggy bank still has electrons in it, we're going to put those on the central atom. If an atom is in the 3rd period or higher, so I'm talking about the 3rd, if you picture your periodic table. Okay, if we're in the 3rd row or higher, so this row, or really I should say lower, right? I'm just talking about bigger on the periodic table. It is possible for that element to have what's called an expanded octet, which is more than 8 electrons. Not thrilled about it, but it will do it as long as it's in that 3rd row, and I'll teach you why that happens in a second. And then you should always double check. Add up your electrons in your drawing and make sure it matches the original value in the piggy bank. All right, here we go. So first step, I just have H to F. So add up the piggy bank. Hydrogen is in the first column, 1 valence. Fluorine is in the halogen, 7 valence electrons. So that means I have 8 electrons to work with in my piggy bank. We're only adding valence electrons because those are the electrons involved with bonding. So we have we have H and we have F. There's no central atom, so I just arranged them side by side, and it says connect them with single bonds. What I would like you to picture is that I'm making you nauseous, is that in that bond, there are 2 electrons. So right now, hydrogen feels as though he has those 2 electrons. Fluorine feels as though he has 2 electrons. They are sharing 2 electrons in that bond. Let's try to do this. Oh, yeah, that's even worse. Sorry about that. Struggle over here. It's still technically spring break, so I can use that as an excuse. Anyways, okay, so we use 2 electrons to make that bond, so I'm going to subtract from my piggy bank 2, so now we're at 6 electrons. So now it says fill outer. So this is where I would put lone pairs on my outer elements like hydrogen and fluorine. But in this case, we know hydrogen is actually very satisfied with the 2 electrons in that bond. So now let's just do fluorine. He has 2 electrons in this bond. He wants 6 more, and we put those as lone pairs. Notice I'm pairing them together. 2, 4, 6, and that makes 8. That's 8 total, but we just added 6 dots, so really my piggy bank is now at 0. It also says to state the type of bond. So I'm talking about that type of bond. What is it? And this is what we learned about on Monday. This is where we look at electronegativities. Your book actually does a good job explaining this as well. But here's what we're going to do. We're going to subtract the difference. So if you look on an electronegativity chart, fluorine is 4.0, hydrogen is 2.1. We find the difference. 4.0 minus 2.1 is 1.9. And what this number says is that this should be an ionic bond. They should not be sharing electrons here. But we do know that hydrogen tends to be part of acids. This is actually an acid, and acids tend to actually kind of act a little bit ionic, a little bit covalent. So I'm going to actually use the fact that we have a nonmetal bonded with a nonmetal to say that it's a covalent bond. So this one, I maybe shouldn't have picked one that's a conflict to start with, but the electronegativity difference says it should be ionic, but because it's two nonmetals, it's actually covalent, and that's such a big difference. I'm actually going to call this a very polar bond, just to make me feel a little better about the fact that maybe they shouldn't be sharing at all and it should be a transfer. It's very unequal sharing of electrons. All right, so next let's try this guy. Nitrogen has 5 electrons. It's bonded to another nitrogen, so that's 10 total valence. I arrange my atoms, and now we start by bonding with a single bond. So now I'm in 8 in my piggy bank because that bond made 2, and now we fill the outer. Nitrogen wants 8, so we have 2 in the bond. That's 4, 6, 8. And so that's using up 8 total, so now I got 2 left. And that means I only have 2 for this guy, so I guess I'll put him right there. Is this nitrogen on the right happy? No. So we said that so now I'm out. If your piggy bank is empty and your central atom, or really in this case, either atom is not satisfied, this is where we're going to do multiple bonds. So here's what's going to go down. I can move these 2 electrons here. And that will make a picture that kind of looks like this. That is called a double bond between the nitrogen. So I just move those 2 dots into the bond right here. And now let's see if they're happy. 2, 4, 6, 8 for this guy. 2, 4, only 6 for this guy. Well, do I have another option? Sure, I can move this guy. And so what we're ultimately left with is nitrogen triple bonded to nitrogen and each have a lone pair. Double check, do I still use only 10 electrons? 2, 4, 6, 8, 10, yep, and everyone is satisfied with a full octet. If we look at bond polarity, nitrogen has an electronegativity of 3.0. 3.0 minus 3.0 is 0. So that means that this triple bond right here is called nonpolar covalent, meaning they are sharing their electrons equally. That makes sense. When 2 elements are bonded together, I would expect them to share totally equal. All right, next we have NH3, which has a total of 8 electrons to work with. We're going to arrange. Usually if you have a singleton like nitrogen, he's your center atom. So I'm going to arrange the hydrogens kind of around him. So now I've arranged. Now I connect everything with a single bond. Notice I'm just connecting the outer elements once to the center. I'm not doing a weird circle thing or anything like that. If there's going to be a ring, it usually tells you in the problem it's a ring, and it's very rare. So in making those bonds, I use 6 of my 8, so I have 2 left. Now we fill the outer. Well, are the outer hydrogens satisfied? Yes, they only want those 2 electrons in the bond. So we go to the inner. Nitrogen has 2, 4, 6. He wants 8. Perfect. I got 2 left in my piggy bank. We'll give those as a lone pair to nitrogen. Now let's do our electronegativities. Nitrogen is 3.0. Hydrogen is 2.1. And again, you can just get those from the table. I think it's 8.3 in your book. Don't quote me on that. So we subtract big minus small. 3.0 minus 2.1. That gives me a difference of 0.9. So that means each bond, notice I'm doing it for each bond individually, that is a polar covalent bond. Okay, that's a polar covalent bond, that's a polar covalent bond, and that is a polar covalent bond. All right, pause the video for me, and I want you to try these. I'm just going to pop up the answers, but I want to see Lewis structures, and I want you to tell me if the bonds in that Lewis structure are polar covalent or non-polar covalent. So polar is unequal sharing, non-polar is equal sharing. Okay, right now I want you to ignore the green slide, or the green writing for a second. We're going to come back and talk about that, but hopefully you got a CH4 molecule that looks something like this guy. and that when you notice that the difference between carbon and hydrogen was only 0.4, that means they're roughly sharing equally. We call it nonpolar. On CF4, you should have gotten something like this. Notice the lone pairs on fluorine, that those are each, so each bond right here, that bond is polar covalent, polar covalent, polar covalent, polar covalent, and then NO minus. So notice when I added up my electrons for this one, I took nitrogens, 5, plus oxygens, 11, or 6 to get 11 right here. But that minus means there's an extra electron added, so plus 1 extra electron, so I actually had 12 to work with. If it is an ion, we always put the Lewis structure in brackets like this with the charge outside to indicate that there was an extra electron, and the difference between nitrogen and oxygen is a polar covalent bond. Again, don't worry about the green yet, I promise I'll come back and talk about that. So for those of you who are wondering where I got the electronegativities from, here's another chart in your notes you can use, or the one in your book. Or if you didn't watch the video that Char made yesterday, you should watch that because he explains how to figure out if something is ionic, polar covalent, or non-polar covalent using differences in electronegativities. Okay, so here's something interesting. What we were doing before is we were looking at bond polarity. So like, are these two atoms who are bonded together sharing equally or unequally? But we can also zoom out and look at the whole molecule and say if the molecule is polar or nonpolar. So if we have a nonpolar bond, okay, that means the difference in electronegativity is 0 or very close to 0. We saw that 0.4 was considered sharing equally, right? So a bond means a nonpolar bond means the electrons are shared equally between two atoms. If I'm looking at the entire molecule, if we have the Lewis structure drawn correctly and all of the bonds are identical, meaning like this is a chlorine bonded to a carbon, a chlorine to a carbon, a chlorine to a carbon, a chlorine to a carbon, right? Those are all identical. Even if those bonds are polar, right, it is possible for them to cancel each other out because essentially what's happening is this chlorine's tugging the electrons this way, right? So that makes it a little bit negative. This chlorine's tugging electrons this way, making it a little negative. This chlorine's tugging the opposite way, and this chlorine's tugging down this way, so they all cancel, so the overall molecule can be canceled out. This will happen, so again, pretend we have a polar molecule, or excuse me, a polar bond like C to O and C to O. This will happen if we have symmetrical VSEPR geometries. We're going to watch a video on VSEPR tomorrow, but just here's like a short list for you of the ones that are symmetrical. So picture, here's Ms. Buller in a tug of war. If I have someone on the opposite side of me, very, very strong, okay, let's say that we have like a strong football player on this side. He's got big muscles, right? And this kid is pulling my arm this way. If it's just him, I'm going to be pulled in this direction. But if I put an equally sized football player on the other side and he pulls me this way, right, they're going to cancel each other out. So even though the bond right here is polar and this bond right here is polar, ultimately what happens is they cancel out when the molecule is symmetric. So you can have polar bonds, but the molecule can be nonpolar. Or you can just have nonpolar bonds and then the molecule is nonpolar. That's an option too. So let's talk about polar. If the molecule polarity shows that the electrons are shared unequally, so the bond is showing that the electrons are shared unequally, we say that the molecule, if this occurs in the molecule, there is a dipole, meaning we have two different poles, right? I'm picturing magnets. So we're going to have a partial positive pole and a partial negative. The symbol for partial positive is like this. The symbol for partial negative is like this. Or sometimes to show dipoles, we do an arrow with the arrowhead representing the negative, and we put a little positive tail, you see that plus sign right there, on the positive end. So when this occurs in a molecule, so we have polar bonds in the molecule and they're not canceled out either based off the shape or the geometry of the molecule, then we get a dipole moment, which is that separation of charge in the molecule. So here's kind of what happens. Here's a water molecule. This is not symmetrical. It's not one of those shapes I listed. Each hydrogen is partial positive and this oxygen is partial negative. So we actually could draw a dipole arrow, yikes, like this, showing that this half of the molecule is negative and this half with the little plus sign is positive. So again, we can do either draw arrows or we could draw the partial symbols. I personally like the arrows better because sometimes when there's multiple polar bonds, you actually see an overall direction. Looking down here, I see two dipole arrows, right? Partial positive, partial negative, partial positive, partial negative, kind of both pointing towards that oxygen. That tells me that this overall molecule kind of has a pole going this direction, pointed towards the oxygen, right? So we get a more partial positive hanging out in this general area and a partial negative up in this general area. Okay, so here are the 6 Lewis structures that I drew and then you tried. I just redrew them here so I didn't have to flip back and forth. But now they're saying, is the molecule polar or nonpolar? And if it's polar, we'll draw a dipole. So we labeled the bonds, but we didn't look at the whole molecule. So first of all, it's very easy if there's only 2 atoms, because whatever the bond is, that's what the molecule is. So in this case, we have 2 atoms, we have a very polar bond, so that means this molecule is polar. So how do I decide who gets the negative and who gets the positive? It's based off electronegativities. Remember, hydrogen was 2.1, fluorine was 4.0. So who wants the negative electrons? Fluorine. So he gets a either partial negative sign, or if we do the arrow, he gets the point of the arrow, and that means hydrogen is partial positive because the electrons are not with hydrogen as much, so he gets the plus side of the arrow. I personally like the dipole arrows best, but I'll kind of show both ways. So now I have a nonpolar bond, 2 atoms, so that's easy. That means this molecule is nonpolar. We do not draw any dipoles, so no partial negatives or positives if it's a nonpolar molecule. I should put that word. Okay, NH3. I have polar bonds. Now we ask, is this, when there's multiple atoms, more than 2, is this a symmetrical shape? Well, it's not one of the base shapes. Again, I know some of you need review on Vesper, but the fact that there's a lone pair on that center atom is a good clue that it's not symmetrical in shape. Nothing is canceling out. So this one is actually a trigonal pyramid shape. So this one, we have polar bonds, is going to be a polar molecule because those polar bonds don't cancel. So if we look at electronegativities, nitrogen is 3.0, hydrogen 2.1. So nitrogen gets the partial negative, the hydrogens get the partial positive. And because, let's see if I can draw, because it's making this trigonal pyramid shape, this is H, and N, the nitrogen's at the top, so that dipole, if I were to draw that in, is actually kind of pointing upwards like this. Picture the base of the pyramid is positive, the tip of the pyramid is negative. All right, next we have a molecule with 4 nonpolar bonds. That makes a nonpolar molecule. Super easy. This guy, we have 4 polar bonds, but if you look, there's no lone pairs on that central atom, so we have to be careful of symmetry. This is actually a tetrahedral shape, so what happens is this dipole is canceled by this dipole is canceled by this one, and so they're all like essentially at a standstill in this tug of war. So we have polar bonds, but they cancel, so this is a non-polar molecule. I'll say symmetrical shape. Dipoles cancel. And last but not least, we have a polar bond, only 2 atoms. That's easy. That's a polar molecule. Oxygen wins that tug of war. It has more electronegativity, so we do my arrow like this. All right, the next 3 are Lewis structures that violate the octet rule. So here's what you need to know. If an element is in the 3p or bigger, so I'm talking about it's any row below 3p, it is allowed to have more than 8 electrons. It's called an expanded octet. How this happens and why it can only happen in 3p or larger is because once we hit 3p, those elements have a 3d sublevel that's readily available that can hold extra electrons. There is no such thing as 2d, so any elements in the 2p sublevel are not able to do that. It actually wasn't a question on the AP exam a few years ago. They had 2 compounds. One had nitrogen in 2p with an expanded octet, and the other one had phosphorus with an expanded octet, and they wanted to know which one was not possible, and it was the nitrogen because nitrogen's only in 2p. So I would like you to pause the video and try these 3 and then check your answers. We're almost done. So here's what I got. The first one, PCl5. Once I single bonded everything, notice phosphorus is in 3p. It is able to take one for the team. He's this guy in the middle. So again, atoms don't like to do this. Don't force them to do this unless they have to. But in this case, phosphorus will take one for the team as long as all of his buddies are perfectly happy. So chlorines all have the 8. So when we filled the outer, we did not have any left over in our piggy bank, so we were good. For ClF3, what occurred was when we filled, so we did our bonds, we filled the outer, and then what happened is we had 4 electrons left in our piggy bank. So the only place that those can go is on the center. Chlorine is in that 3p sublevel, so it is allowed to have its extra 2, 4, 6, 8, 10 electrons. Same thing with xenon. Once we made our single bonds and then we made the outer satisfied, our piggy bank had 2 left over, and so we now have a xenon with those extra 2 electrons. All right, pause the video and you try this one. Remember, Be is okay with 4, hydrogen's okay with 2, and boron's a moron, he's okay with 6. Check your answers. Hopefully this is what you got. We had an expanded octet. We had beryllium with just his 4. We have an expanded octet, and then don't forget that negative sign. It means there's an extra electron, so we have to put the whole structure in brackets with that minus charge. If you take more chemistry in college, you're going to have to take organic chemistry, which is the chemistry of organic compounds, my favorite type of chemistry. But we're not going to spend a ton of time on this, but I just want to let you know that a lot of times organic molecules are chains, so they're carbon-based chains, and the formulas are actually written in a way to help you figure out the structure. So instead of grouping all the carbons together like C3H whatever, they actually write it more expanded to help you. So for example, CH3, that's telling me that those H's belong to that carbon. Then we have COOH. Anytime you see a C and then an OOH, it's usually going to be the C with an OH group and then double bonded to the oxygen. If I added up my piggy bank, I would notice that I had 4 left over electrons, and oxygen is the only thing that's not happy. You can double check all my bonds. Again, you don't have to memorize that this CHU, right, is a double bond and then the OH, but I just want you to start to recognize some of these structures. All right, here's another one, CH3, so those H's belong to this carbon, and then we have CH2, so this guy has 2 H's that it belongs to, and then another CH3. And notice everybody's satisfied. Again, I'm not even adding up my piggy bank, but if I did, I think you would find that I used all the available electrons. Here's another one, CH3. And then I have a C with an O, so that means there's some sort of O hanging off of this, and then another CH3 group. Anytime we have an O in the middle of the molecule, you're going to usually need a multiple bond. Again, if I had added up my piggy bank, I think you would have found that I would need that. I don't have enough electrons to give carbon a lone pair and oxygen 3 lone pairs, but it is pretty common to have an oxygen double bond. And then the last one. Notice this guy has an H in the middle, so it's CHO, whereas this one had the H on the end. The way that works is this carbon has the hydrogen and its own oxygen. So when the hydrogen belonged just to the oxygen, it came after. When it belonged to the hydrogen, it came after. When the hydrogen belonged to the oxygen, it was after oxygen. When it belonged to the carbon, it was directly after the carbon. Again, you will not have to draw from scratch structures like this, but the AP exam will give you some backbones to help you visualize. So I'll actually show you an example next. So this is the HNO2 molecule. This was on the AP exam in 2018. So we need to draw the Lewis dot structure. Here's what you're going to find. There are 18 electrons. And so here's kind of what our options are. I can take H, O, N, O, and I have 2, 4, 6. I got 6, so I have 12 left. And now my hydrogen's good, but if I do my oxygens, that's 6, so I only have 6 more. Only have 2 more. None. So what I notice is oxygens are good, hydrogen's good, but not my nitrogen. So we need to make a double bond. Here's what I see. We have 2 choices in the matter. We can move this guy and form a double bond. Or we can move one of these guys. Oops, excuse me. Wanted to do green. Or we can move these guys. And so then we'd have H, O, N, double bond. There we go. So remember when I told you that you have to make sure everybody contributed their valence? So remember, oxygen to my piggy bank gave us 6 valence, and nitrogen gave us 5 valence. So again, everybody wants to feel 8, but they also want to be in close contact with those electrons. So here's kind of my example, or I'll like point it out for you. I want that to be smaller. There we go. So on this guy, oxygen is feeling 1 in here, right? I know it actually feels 2, but like hydrogen contributed the other electron in that bond. So let's say that red dot came from the oxygen. 2, 3, 4, 5. So he feels 5 of his valence. Yes, he feels like he has 8. You with me though? Okay, whereas this oxygen, 1, 2, 3, 4, 5, 6. So he feels like he gave 6. Nitrogen gave 5. 1, 2, 3, 4, 5. Feels 5. 1, 2, 3, 4, 5. He feels 5. And lastly, oxygen, 1, 2, 3, 4, 5, 6, 7, feels 7. And this guy, 1, 2, 3, 4, 5, 6, feels 6. So there's one structure that actually is a better representation, right? Again, and when I say feel, remember, they all feel like they have 8, but I'm talking about the ones they contributed. Like, if I'm going to donate and contribute to the group funds, I don't want my money to get, or my electrons to get too far away from me. And so I would argue that this structure is the correct one because oxygens both feel or are very close to those 6 they donated, and nitrogen is the 5, whereas this one, oxygen is kind of losing out. Right? So we're going to use this structure here. And a good rule of thumb, if I just kind of lost you there, is that oxygen really likes to have 2 lone pairs and 2 bonds, whereas nitrogen likes 1 lone pair and 3 bonds. You'll see that combination a lot. I'm going to get to a more kind of structured way of figuring out if there's 2 different options, what's best. But before we do that, let's talk about the types of bonds. So first, a single bond is when there's 1 pair of electrons being shared. It can also be called a sigma bond. A double bond is when we share 2 pairs of electrons between the atoms, and that is made up of 1 sigma and 1 pi bond. And then a triple bond is when we're sharing 3 pairs of electrons between the 2 atoms, and the way that forms is by using 1 sigma bond and 2 pi bonds, and we're going to learn more about sigma and pi a little later this unit. Carbon, nitrogen, oxygen, phosphorus, and sulfur are most likely the elements that you will see forming multiple bonds. Again, we don't do double bonds or triple bonds unless we have to. It's like a last resort situation. But the combination of sigma and pi bonds are stronger than sigma alone. And pi bonds are weaker than sigma, but they can't exist alone. Like I can't have a double bond without first having that single bond, right? So for it to be a pi bond, or for it to be a double bond, I need to have a sigma and a pi. The length of the bonds also changes. If you picture a rubber band, a single bond is like when you stretch a rubber band. If you double the rubber band up, girls, you know how this works with your hair ties, right? If you double up the rubber band, that's a double bond, and that's much shorter. You can't stretch it as far. And triple bond, if you triple your hair tie or you triple your rubber band, it's much shorter. You can't stretch it as far. So triple bonds are the shortest, single bonds are the longest. Okay, so last topic is resonance structures. So resonance structures are different in that the electron pair assignments are different, so not the atom arrangement. They're all arranged the same way, kind of like the example we just did from the 2018 AP test, but it's where the lone pairs and the double bonds are. So here's what we do. If there's resonance, you have to draw all the structures, and the AP usually says draw with resonance. What we do is we put an arrow in between the options to indicate that there's resonance. So these structures that you're looking at are both ozone, and studies show that ozone has 2 bonds of equal length, but obviously there's a double bond and a single bond in these resonance structures. So what actually occurs is the bond length is an average of the resonance structures. So what we have discovered is that ozone is actually 3 oxygen molecules with an average bond length about like somewhere in between a double and a single bond. So here's my example. Draw the resonance structures for CO3 2-. This guy's got 24 total electrons. 22 of them came from the C's and the O's, and then the 2 extra. And so we put my C in the middle, my O, my O, my O. When we do single bonds each, what I'm going to find is that I don't have enough to make the carbon happy. So I'll show you real quick. There's all my electrons. My piggy bank is empty, but my carbon is not satisfied. So what do we do when your central atom does not have 8 and your piggy bank is at 0? That means we need to do a multiple bond. So I'm going to take 2 from here, and I'm going to make a double bond. So we'll just erase real quick. And so I took those 2, and I made a double bond right here. Okay, I need my brackets and my -2 charge. So now we draw another structure. Well, I happen to pick the top oxygen, but couldn't it have been this oxygen down here that had the double bond? Absolutely. So now this guy gets 3 lone pairs. This guy only gets 2. This guy keeps all 3. -2 charge, that's the world's worst bracket. And we do the third structure because we can't forget this guy. Single bond, double bond, single bond. So there are the 3 resonance structures, and so we would find that this CO3 2- polyatomic ion would have a bond length somewhere in between single and double, probably closer to single because there's 2 single bonds and 1 double bond. So the 2 examples we looked at were equivalent structures, right? There was no actual difference between those 3 CO3s that I drew, but the AP exam question where we were looking at the 2 different options, those were non-equivalent Lewis structures. So what happens if they're not just easily, obviously all the same thing, just me choosing which oxygen to double bond, but they're different choices, right? Do we double bond the inside nitrogen or the inside oxygen or the outside oxygen? What we do is something called formal charge, and it's the difference between the number of valence electrons on the free element and the number of electrons assigned to the atom, and we can use it to figure out the most favored structure. So here's what we really do. It's a simple calculation. We're going to take the number of valence electrons that element has, that's not my highlighter, minus the number of valence assigned, and to get the number of valence assigned, it's really the number of lone pair electrons plus half the bonds, half the number of electrons that are shared in the bond. So let me show you an example. Oh wait, here's how we pick. So some rules. When the sum of all the formal charges, so you would give a formal charge to every element, that has to equal the ion's charge. And here's how you decide what's best. You want every atom to have 0 ideally, or as close to 0 as possible. So a formal charge of 1 is better than a formal charge of 3. A formal charge of -1 is better than a formal charge of -2. And then a molecule is stable when the negative formal charge is on the most electronegative element. So now let's look at an example. So it says, draw all possible structures for the sulfate ion and decide which is plausible using formal charges. So sulfate is SO4 with a -2 charge. It has 32 electrons for us to work with. So first of all, don't even look at the green. Sulfur is in the 3rd row or lower, so it's able to have an expanded octet. So right off the bat, I've pictured that we could have 4 single bonds, right? Or we could have 3 single bonds and 1 double. Or we could have 2 single bonds and 2 double bonds. Or we could have 3 double bonds and 1 single bond. Or we could have all double bonds. In my mind, these guys have resonance with them also. So these are all resonance structures for sulfate. But this guy, couldn't I move the double bond there or there or there? And then this guy also has plus resonance, because we could have the 2 double bonds there and there or right next to each other, right? There's different combinations. And same with this guy. We could move essentially that single bond around so that we have 3 and 1. But I just figured if I drew one of each, we could figure out at least which strand would be best and then draw the rest. So sulfur, remember we're going to take the number of valence minus the number of lone pairs on the drawing plus half the bonded atoms. So on this first one, sulfur has 6 valence assigned to it. There are no lone pairs on the sulfur, and there are 8 electrons assigned to it in bonds. So 6 minus 0 plus half of 8 gives us a +2 formal charge. So he is +2. Oxygen, this oxygen right here, has 6 valence electrons assigned to it. In the drawing, it has 6 lone pairs and 2 electrons in the bond. So 6 minus 6 plus half of 2 gives us a -1 formal charge. That is the same for all of the oxygens because they all have 3 lone pairs and 1 bond. On this atom, we have 6 valence electrons for sulfur, no lone pairs, but now there's 2, 4, 6, 8, 10 electrons assigned to it, a +1 formal charge. Oxygen, let's do the oxygen that is in the double bond first, this guy. He has 6 assigned to it. He has 4 lone pair electrons plus half of 4 because there's 4 electrons in the bond. Gives this guy a formal charge of 0. That's good. We liked zeros. And then we do the single oxygens. You'll find that these guys always have a -1, just like the ones over here. So -1, -1, -1. Same thing on this guy. What we're figuring out is that the oxygens with the double bonds have formal charges of 0. The ones with the single bonds have formal charges of -1. So I'm going to do that for all of these. Oxygens that are double are zeros. Oxygens that are single bonds are -1. And then for the sulfur on this guy, the sulfur is actually at 0. So when sulfur has those 12 bonded electrons and no lone pairs, it has a formal charge of 0. So this guy's looking pretty good because that's the first time we've seen sulfur at 0. On this one, our sulfur is at a -1, and at this one, it's at a -2. So the best structure that we could probably pick and draw the resonance, all of the resonance for, I would say is this guy, because we are getting essentially almost all of the atoms to 0, and the negative charges here and here, which we have to have, they have to add up to that -2. Those are on the the most electronegative elements. I would rather have the oxygens with negative charges than the sulfur with a negative charge, because if the oxygen has a negative charge, that's most likely because the oxygen's more electronegative. So what I could do is I could say that this is the best structure, and I could draw the different resonance choices for this one. But that's how we calculate formal charge. You'll see some of it in your book problems as well. Alright, I am so sorry that was the world's longest video. I thought about cutting it in 2 and then decided to power through. But this is what we would cover in one class period, so just trying to keep you guys on track for the AP exam. Talk to you later.